Hi everyone, this is Jesse here from SkyCiv, and today I just wanted to show a design example looking at how we can use the Quick Designs module for timber connections to design a bolted connection to the Australian standards. So the first thing I'm going to do is I'm going to open up the Quick Design library, and I'm going to search for the Timber Connections tool. We can see here we've got the Timber Connections tool, and I'm in the Australian standards, so I know this is the Australian version of the tool, and I'm going to open that up. I'm just going to do a quick run of the defaults here so we can see everything that we get when we run our values. The first thing we have on the left here is we have our inputs. We can see it's not too many inputs, so we'll be able to fill this in quite quickly for our design example. And when we run with our design example, what we're going to get is a report in the center that looks like this. This just shows all our input values that we've used to construct this example. It shows the diagrams as part of this example as well, and then the calculations to get our final result. And finally, on the right here, we have the summary of our outputs. We can see the first one is the design action that we have being applied to our connection. We have this value down here, which is the capacity of the entire system. And we have the utilization, which is the force divided by the capacity. So 1 on 1.17 gives us this value of 85%. We also have this additional value here to help show how the system is working, which is the capacity per fastener. So in this case here, in this design example I run, we only have one fastener. So the capacity per fastener is the same as the capacity of the system. But we can see how this value might help us in future if we wanted to add extra connections to get increased capacity if our utilization was unsatisfactory. Now, what I'm going to do is I'm going to start putting in the values for our design example. The example we're going to be looking at today is example 7.2 from the HB 108 textbook. And this example is for the design of a bolted truss connection. So bolted truss connection, we're going to be using our fasten type as bolt. And for this truss, we have our member in double shear. We're going to have a top chord member in the center. This top chord member is going to be inclined at 30 degrees to our horizontal members at the bottom, of which we're going to have two members on either side of that interior top chord. So the design example also tells us that the force we're going to be using is the force inside this top chord. So what we're going to do is we're going to incline the load to be in the same direction as this member here. And so we can see in this design example, this is exactly what our truss looks like and what it looks like in this design example. And of course, we have some supports at the bottom here, but for the purpose of our calculation, the only force we really need is the force in this member, which gets applied to this bolt, and it gets applied to this member, but we don't really need to worry too much about how these forces are moving about. We just need to know this force we want to apply on the connection here. The next thing we want to input is our geometry. So what I can do, I'm just going to minimize that, and we can also minimize this if we wanted to. But actually I'm going to leave this one open because for the geometry we're interested in this T1 and T2 value. So T1 is the thickness of our horizontal members. These members are 140 by 35 members, so we can change this to be 35 mils thick. And for our T2, our top chord member is a 140 by 45 member, so we can change T2 to be 45 mils thick. For this design example, we have two fasteners, and these fasteners are we have two rows of fasteners. So here we can see a number of fastener rows is talking about the number of bolts that we have, or rows of bolts that we have perpendicular to the direction of loading. So that means if we have our direction of loading going this way, our extra bolt would be along this member, somewhere like here or something like that. So in this case, we do have two rows of members. For our bearing, we're not going to worry too much about bearing in this example, so we can just skip over this. We have M12 bolts, and we don't have any fastener plates. We could also just choose no fastener plates if we wanted to be conservative. And for this example, we have seasoned black butt timber. So seasons, we can search in black butt, and that's going to automatically apply the joint group. So the joint group is just basically the strength related to this type of timber. And this is species dependent. It's not like member design where you have F grades. In this case, the strength of the joint is more dependent on the species. If we had something that's not included here, we could use a custom joint group to just manually toggle between these different joint groups. But in our case, we can just use blackpot because we know that's our species of timber. We finally just need to put in our loading duration. So this is going to be related to the phi factor for these first two values. So in this truss, because it's a truss, it's going to be a primary joint. If any member fails, like the whole thing's going to fail, so it makes it a primary joint. And we are in a building which is a restaurant, and the area of the impact is greater than 25 meters squared. For the loading duration, we're told we have a 5-day load, and design action is 18.6 kilonewtons. So now we've got all our values input, we can press run, and we can see our summary report that we get here. First thing we have is just the inputs that we've just gone over just now. This is just a summary in case you wanted to print that report and share it with someone else. You'd have all those values and you'd be able to reconstruct this example later on. Next, we have our diagrams that we've seen on the left here as well. And finally, we have our the start of our calculations. So the first thing we calculate is just the factors, like our intermediate factors that we need. These factors just generally come from smallish clauses in the standard, and they can be related to different things. The K1 factor is one of the most common factors for timber design, and that's just related to the duration of loads. So in our case, for our design line, we've got a 5-day load, and that directly controls our K1 factor. We have the factor for metal side plates, K16, which would be directly related to this. Do we have a fastener side plate? If you had a metal side plate, this K16 value would be used to show the strength increase by having that side plate. In this case, it's just 1. And then we have a factor for multiple fasteners. In this case, it's just 1. In the design standard, the way that the strength of the timber members is categorized is using this QSK value. And this comes from a big table which relates to joint group and the thickness of the timber, as well as how these timber members are arranged. So this quick design module will automatically interpolate these values from the table. So if you had a width that's not inside that table, you'd use interpolation, and that's automatically handled by this calculator. It's a bit hard to do manually in the table, or a bit tedious to do at least in the table. And so from the tables here, we can see we've got our different tables, 4.9a, 4.9c, 4.9a, for example. From these tables, we get these different values. So we get the strength parallel to the timber member for this thickness of 45 millimeters, that's for our internal member. And we get, for our external members, with the total thickness of 70 mils, we get the strength perpendicular to that member. Now, what's going to happen here is, so for the internal member, we have the force only parallel to the load. So in this case, for the inner member, it's quite simple that the capacity is just 28 kilonewtons. But for the outer member, the load is inclined in a direction that's not parallel to the member and not perpendicular to the member. And so we need to use what's called Hankinson's formula to get the effective strength of those timber members. And from that, we get a strength of 25 kilonewtons. And we can compare the strength of the outer member and inner member and take the most critical member capacity. In this case, it's the one for the outer member. And we get a strength of 25 kilonewtons. We finally can do our final capacity calculation based on this clause here, where we just multiply most of the factors that we found to get our strength. So we've got our phi factor, our other k factors that we found, n being the number of connections, and QSK being the strength that we found for that timber member. And from this, we get a total strength of 30.8 kilonewtons and a utilization of 60%, which is the exact same as what we had in the design example in the textbook. So we can see how easy that was. We just put in our inputs here, and we can automatically run through and find really effective and efficient design by using this automatic table interpolation. We can get a nice summary here on the right, and we can get this nice report that we could present to others. The final thing I just skipped over a bit was we also get spacing and distances here. And so these are values we just use for detailing. This would just be something we double check when we detail our member, just to make sure we're spacing these bolts out to meet those minimum requirements of the standard. So thank you for watching this video. If you had any questions, you can click on this chat box here. You can message us and we'll get back to you as soon as we can. Otherwise, I just recommend to have a play around with the tool, play around with the quick design library, and see how you go. Thank you.